נצרף את זה כאן, זה בסדר. אוקיי, יודעים, תנו לי רגע לבדוק משהו, בסדר?
אני יכולה לבדוק אם כאילו לא נמצא לעשות, זה יכול להיות... תראה, יש אצלס פה בקומה, זה בתחילה כאלה שלוש.
אני רוצה לעשות שם מאוד חשוב. אז תעשי ספס.
בסדר. Okay, so today we will talk about canonical ensemble. Okay, so last tutorial you saw that in microcanonical ensemble, right? Yes, right? We talked about microcanonical ensemble, and we saw that for working in microcanonical ensemble, we need to have a system with constant energy. Okay, and now we are continue to canonical ensemble, where we assume, okay, we still work with constant energy as in the microcanonical ensemble, but here we also assume, okay, let's do it like this. We assume a system, a big system with constant energy, and then we say, okay, let's say that this system with the constant energy, yes, constructed from many, from a small system, okay, some small system, and from a, let's call it, okay, this will be single system, okay, and this will be set of systems. Okay, we still assume that the energy is constant in the big whole systems, but then we say, okay, let's look at one system in this ensemble, okay, and then we can say, okay, so for this system we don't need a constant energy, yeah, it can exchange energy with its surroundings, okay, and then we can say, okay, the rest of the systems are like bath heat bath, yeah, okay, and then from those assumptions we can define a partition function that will describe the single system in a bath heat. Okay, so we still take in consideration the constant energy when we build the partition function. Okay, so if we take all of this assumption into the partition function, okay, we get that we can write the partition function as summation on exponent of minus beta and the energy, okay, where we are summing on all different states in the system, all possible states.
How do you reach this conclusion?
Wait a minute. Okay, so this you saw in the lecture. Okay, I can. Okay, I can upload to the Moodle some of this derivation. Okay, so this is our partition function where we're summing on all possible states. Okay, not all possible energies, all possible states. If we have two states with the same energy, we have two items in the sum. Okay, because we're summing on all the states, not on the energies. Okay, and if this is our partition function, then we can use it to define thermodynamics sizes. Okay. So we're starting with if this is our partition function, if this is the description of the system, so the probability to be in state R, okay, that will be 1 over the partition function. Okay, the partition function is some constant. 1 over the partition function times exponent minus beta times the energy of this state. Okay, so as our energy decreases, we have more probability to be in that state. Okay, that makes sense. Okay, and if this is a probability to some state, then we can start to talk on average sizes. Okay, so we can talk on average size of energy. Okay, so this will be summation on all possible states, and we sum in on the value of the energy times the probability to get that energy. Okay, the value of this state times the probability to get this state. So at total, we have the probability. So we have summation on R, ER, and we have exponent of minus beta ER divided by Z, and Z I can write outside the sum because it's a constant. And I can write it as minus derivative of ln Z relative to beta. Okay, if I take the ln of the partition function, I will get exactly this size. Okay, good. This is our internal energy, what we calling U. Okay, and as for the energy, we can do it for any size of the system. Okay, so we can have the square of the energy, and that will be 1 over Z, second derivative of ln Z relative to beta. Okay, we have the pressure, okay, that we know equals to derivative of U by the volume, okay, and we have U as function of the partition function. So that will be equal to 1 over beta derivative of ln Z relative to V. And we can write the Helmholtz free energy is U minus
ts, and that will be equal to minus kb t ln z. Okay. Okay, so last week we saw that we can use microcanonical ensemble, right? If in the question we have a data that we have system with constant energy. Okay, so here in the canonical ensemble, so the big assumption is ensemble of systems with constant energy. But when we look at one system, okay, we don't need to see the constant energy because the system exchange energy with its surroundings. Okay, so even if we don't have the sentence that say as constant energy, we still can use the canonical ensemble. Okay, because we are assuming a heat bath around the system. Okay, so now let's talk on, so this is general partition function, and now we will talk on partition function of subsystem. Okay, בעברית זה פונקציית חלוקה חד-חלקית. So the general partition function, yeah, if let's do it now for a continuous system. Okay, this was for discrete system, now for continuous system. So it's the same, except that instead of a sum, we have an integral. Okay, so we have an integral of exponent of minus, let's write it, minus beta e. Okay, and this energy depends on the places of the particles and their momentum. Okay, and here, as in the microcanonical ensemble, we have some constant that helps us to keep the units of the partition function good for the rest of the thermodynamic sizes. So we have here Hfs, H0 in the power of n, where n is number of particles in the system. Okay, and now what I want to say is such a thing. So, assuming we have not only one type of particles in the system, okay, we have several types of particles. And let's say that each particle doesn't depend on the other, meaning we have some ideal gas. Okay, each particle has its own energy that doesn't depend on other particles. So we can write this integral as a single integral on one particle, yeah, for its coordinates, okay, because we can divide the integrals. So we have integral of exponent of one particle, so we have here x, y, z, and px, dy, z. Okay, and we have n similar integrals for each particle. Okay, so instead computing this shared integral for all the particles, I can write, okay, this will be equal to the integral of one particle in the power of n, because I do it n times for n particles. And then I can write that the partition function is the subsystem partition function, okay, for one particle in the power of number of particles. Partition function that is for one particle.
So Z describes a subsystem of a system, and the other one describes the
Subsystem of the subsystem. Yes,
Okay.
but yeah.
Each particle in the subsystem.
Yes, but the subsystem we're talking for Z is just for the theoretical idea for or how we reach this function. Okay, so from now the function of Z, the system of Z, is our main system. Okay, and then if we have n particles in Z, we can describe it with a subsystem partition function. Okay,
Just
for one particle.
For systems where you can neglect the internal interactions
Yes.
of the particles?
Yes.
Not for every system.
No, if we have interaction between particles, we cannot do this.
Okay.
We
So
cannot
not
write
really.
this integral. Okay, and in general, so we can write it. Yes, now if we have not only n particles in the system from the same type, that their energy described the same. Okay, if we have different types of particles, that their energy described differently, okay, but still as an ideal gas. So we can write for each type of particle its own subsystem partition function. And then we can write the total partition function as multiplication of, let's write it as Zi. Okay, this is a partition function for all particles from specific type. So this is, let's write it, partition function for all particles from type I. And then the partition function for all particles from type I, that will be equal to the subsystem partition function for one particle from type I in the power of the number of particles. And if our particles are identical, okay, as we did in the microcanonical example, we need to divide by n factorial. Okay, and we can do those steps only if we're talking on particles that have behavior of ideal gas. Okay, if they are not interacting.
So if they do interact, we just need to use the wall Z function.
Yes. Okay, so that's fine for now. Great, let's do examples. Okay, we'll start with a short one and then do exam question. So, example 1, we have a 3-level system. Okay, so we have a system n distinguishable particles has 3 energy levels for each particle, and the system is described by the Hamiltonian h equals to minus h, sum from I equal 1 to n of Si, where Si equals minus 1 or 0 or 1. Okay, so we have a system with 3 energy levels, okay, where Si can be minus 1, and then we have a level energy of H, and the Si where it's 0, so we have 0 energy level, and where Si equals 1, we have minus H energy level.
And the n is the number of particles.
What?
N is the number of particles.
Yes. Okay, and then for each particle it can be on the energy level of minus H, 0 or H, and the total energy of the system is summation on all particles. Okay. So we have a discrete system. And we see several things. So in the energy term, okay, we see that the energy for each particle depends only on that particle. Okay? The energy of particle I doesn't depend on the energy of particle, some other particle J. Okay? So first, the particles are not interacting. Great. The second thing we need to pay attention to is that the particles, okay, are different. So we can identify each particle. Okay, what we want to do, we want to find the free energy of Helmholtz. Okay, so so what we know here, okay, of course we are in the canonical example tutorial, but let's see why we use the canonical example. So first we see that the energy of the system is not constant, right? So that means we cannot use the microcanonical example. Okay, next thing we see, in the next tutorial we will see another example, but here we see that we have constant number of particles in the system. Okay, the system always have n particles. Okay, that means constant particles means that we use the canonical ensemble. Okay, so we have changing energy that means that we don't use microcanonical ensemble, and constant particles, so that means canonical ensemble. Okay, so we want to write the free energy of Helmholtz in the canonical ensemble. Okay, so we know that that will be minus kb t ln of the partition function. Okay, that means that we need to find the partition function. Okay, so we start to write z equals to. Okay, and now because we know that the particles not interacting, okay, we can write it with the subsystem partition function. Okay, so we can say that will be the subsystem partition function in the power of n. Okay, and we not need to divide by n factorial because the particles are distinguishable.
So if they are not distinguishable, you need to divide by n factorial.
Yes.
Why?
Because we don't want to sum on the same state several times.
Okay.
Okay. Okay, so now we need to calculate the subsystem partition function for one particle. Okay, so we write that will be equal to sum on all the states, yeah, of exponent minus beta e, but all the states here are all the states for one particle only, okay, not all the states of the system, but only on one particle. All the states for one particle. Okay, what are the possible states for one particle in this system?
H0 and minus H.
Okay, yes, so the energy can be equal to right, minus H, or 0, or H. Right, this is the energy the particle can get, and those are all the states it can be in. Okay, again, we're counting states and not energies. Okay, in this case, the states have different energies. Okay, so we sum up on those values, and we get that zeta equals 2. So we have E, and we have beta H plus 1 plus E minus beta H. Okay, that is for E equals minus H. That is for 0. And this one is for H. Yeah, okay.
So it's like a hyperbolic cosinus. 2 times.
Yeah. So we can write the total partition function as z equals, and we convert it yet to hyperbolic cosinus, so we have 2 of beta H plus 1, and we have in power of n. And this is our partition function. And then all we need to do is take this partition function and insert it to the free energy of Helmholtz. So we get that F equals to, so we have minus kBT ln of, or we can write it, yeah, minus kBTN ln of 2 hyperbolic cosinus beta H plus 1. Okay, and this is the free energy of Helmholtz of the system. Great. So this is a pretty easy question. Okay, let's now move to exam question. Okay, so now we want to see, okay, so sometimes we have, most of the times, we have complex system, okay, that we cannot do this straight thing and use the subsystem partition function and all is okay. So most of the times we don't have this. Sometimes we will need to do some, let's say, algebraic games to get this separation between the particles, to get that they are not interacting, despite that in reality they are. Okay, in a mathematical way, we want to get to some term where we can use this subsystem partition function. Okay, so the question is a little bit long, so okay, let's write it. We have a string composed of n similar masses of size m. All the masses are lined up one on top of each other. Okay, so we have let's say we have a floor, okay, and then we have a line of masses. And okay, and they are connected with a string. Okay, someone let's say pulls the masses up. Now the distance between the first mass to the floor, okay, can take the values of, let's call it R1 equals to sum y0 plus n1h. Okay, and the distance between sum mass I and mass I plus 1 can be, and we denote it R1, Ri plus 1, and that equals to the same y0 plus we have here n I plus 1 h. Okay, so it takes the same form, and those n's can run from 0 to infinity, and this edge is some constant that's bigger than 0. Okay, so now extension energy from this string between the masses denotes by Ni times epsilon 0, meaning as n is bigger, the distance is bigger, so the extension energy is greater. Okay? Great. Except for extension energy, we also have gravitational energy. Okay, so that will be mg, and let's call it yi. Okay, what is y? Y is the height from the mass I to the floor. Okay, okay, and now we want to find the partition function. Okay, so this is not a simple question because we have interaction between the masses. Okay, each mass height depends on the height of the mass before it. So how do we do it? Okay, so we start with writing the partition function in general. Okay, this is 5 points, so equals to states, and we have here E minus beta E. Okay, fifth step. Now we want to find dc. Okay, what is the energy for some state? Okay, so the energy so we have in the energy the term of the extension energy. Okay, so we have summation on all the masses and their extension energy. Okay, and then we have the gravitational energy. So we have here mg yi. Okay, what's this yi? So here our particles are not interacting. Okay, we need to somehow solve this term. Okay, so what is our height of some mass? Okay, so yi equals to the distances between all the masses up to the floor, down to the floor. Okay, so we sum up on all the distances between the masses from the first mass to our ith mass. This is the height of mass i.
אני יכולה להטעין את האייפד?
לא,
אני חייבת להטעין את
אנחנו עוד כמה דקות מסיימים ואז תיכנסו, כי אחרת זה יפריע לנו. Okay. Great. We know what are those RJs, so we can write it as sum from j equals to 1 until I of y0 plus njh. Okay, so our energy E equals now to the extension energy plus the summation on this summation. So we have here sum on I, we have mg and summation on j from 1 to I, y0 plus nj h. Okay, let's continue. What is the summation on y0? So y0 is a constant, right? So we can write, instead of the summation, we can write it as y0 times I. Okay. And let's see what this gives us. Okay, so we have here summation on I, summation on j from 1 to I on nj. Okay, so let's write it all the summation in really in 1 plus 2 plus 3. Okay, so this is equals for I equals 1. Okay, this is equals to n1. Okay, and then we continue. For I equals 2, we have here plus n1 plus n2. Okay, for I equals 3, so we have n1 plus n2 plus n3. Okay, and so on. So this summation, we can see that we can write it as n times n1. Yeah. Okay, you see it? And n minus 1, n2, and so on. Okay? So this is really equals to summation on I of n minus I minus 1 times n1. Okay, and what we've done here that we don't have anymore the dependence of J on I. Okay, the interaction between the masses. So now our energy can be written as, so we have epsilon 0 summation on I of Ni plus we have here mg y0 summation on I. Okay, and we have the last one, this one, so we have sum on I of n minus I minus 1 and I. What is this one? This is from the y0 integral.
So it's y0 times I.
Yes, so the y0 is constant, so write it outside the sum. Okay? Okay, so okay, we have another 1 minute. Okay, we can do it. So this summation we know how to solve. 1 plus 2 plus 3 plus 4. So this is equals to n plus 1 divided by 2. So our energy term becomes to be this constant mg y0 and n plus 1 divided by 2, and now we have a summation on, okay, we have here something nh and n minus 1 plus I times ni. Okay, so now we can write for each particle the contribution of the energy he gives to the system. Okay, and then we can use the subsystem partition function. Okay, so we can write that the total partition function that will be equal to, okay, so okay, we have here in the energy the dependence on the number of mass. Okay, so we cannot say those are the same masses with the same contribution of energy to the system. So we actually need to say that they are different masses, as different particles, because their contribution to energy is different. Okay, so instead to write subsystem partition function for one particle in the power of n, okay, we need to write it as multiplication of partition function for each mass. Okay, and then we take our formula to partition function, insert the energy, and solve for one particle with one summation. Okay. Fine. Good. That was it.
Can you give another example?
To which part?
Why do we need to make a difference between particles?
Okay, so let's do such a thing. So our tutorial is over, and now let's go to Hebrew, okay? אז ככה יותר פשוט להסביר. אוקיי, אז כן, למה התייחסנו כחלקיקים שונים?
כאילו למה הפרדנו אותם?
למה עשינו את כל החלק עד כאן, או...
לא, עד כאן בסדר, למה היינו צריכים להתייחס אליהם כחלקיקים?
אוקיי, כי אנחנו מתייחסים אל חלקיקים כאל חלקיקים זהים, אם התרומה שלהם לאנרגיה מתוארת באופן זהה. אוקיי, אז פה בגלל שיש לנו את ההשפעה של האינדקס של ה-MI, אוקיי, אז כאילו כל חלקיק בעצם משפיע באופן אחר על האנרגיה. ולכן מבחינתנו הם לא חלקיקים מאותו סוג, כי ההשפעה שלהם שונה. אוקיי, אז אנחנו רושמים את זה ככפל ולא כחזקה. עכשיו גם אם ניקח בדיוק את האנרגיה הזאת ונציב בתוך הנוסחה הכללית, כן, אם פשוט נציב את זה, נאמר נתעלם רגע מזה ופשוט נציב את זה בתוך E מינוס בטא E, אנחנו נקבל בדיוק אותו דבר. יש לנו פה איזשהו קבוע בסדר, אבל נקבל כפל לפי ה-NI השונים. אוקיי, ואז בעצם פה אנחנו סוכמים על ה-NI השונים.
אבל עבור כל חלקיק בפני עצמו המסה שלהם כן זהה.
המסה זהה, אבל בגלל שהם נמצאים במקום אחר בשרשרת...
זאת אומרת, האנרגיה כאילו שונה.
כן, בדיוק.
אוקיי.
כן. תודה. בשמחה.
מה זה?
סוף הזמן של מכניקה. צריכים לפלס דרך. לפני שנפלסו דרך דרכנו.